Alright, guys, welcome back. It's been a while. This is Ultimate Guide to Sketching Almost Any Graph, Part 2. So, today we're going to be focusing on graph sketching, specifically for interviews. So, this is applicable to anyone that has interviews coming up for subjects like maths, chemistry, physics, economics, stats, any sort of degree that has a heavy maths component. This might be really useful, but probably more so useful for people doing maths or like maybe physics. So do take that with a pinch of salt because we're gonna get into quite technical things here. So yeah, any prerequisites? Yes, if you haven't already watched part 1, please do watch part 1 because we're just going to build on stuff that I talked about in part 1, and then there's going to be some new stuff as well. So yeah, I guess let's get straight into it. So the first thing I wanted to talk about was exploiting periodicity of trig functions. So what do I mean by periodicity? Well, trig functions are periodic. So for example, if we take y equals sine x, the period is 2 pi, right? The sine x graph repeats every 2 pi. Which means if we sketch a graph, say for example, y equals, I don't know, x sine x. I don't know what this looks like. But for some restricted domain of our graph, or it might be the whole domain, our function will have some sort of oscillatory behavior because the sine function is periodic. And so we can exploit that fact. We can use that to kind of guess what the shape is going to be like. And we'll come on to looking at that in the example later on. So we need to bear that in mind. And also, we can use the fact that the trig functions, well, some of the trig functions, their range is bounded. So the modulus of sine x is less than or equal to 1 for all real values of x. And that's the same thing with cosine x. So mod cosine x is less than or equal to 1 for all real values of x. Right? Oh, pen's not working again. There we go. And both of those things just mean that cosine x and sine x are between -1 and 1. Okay? So we can use that fact because if we have y equals x sine of x, right? We know that we're going to have the graph of y equals x, but we're going to be multiplying the graph by a real number between -1 and 1. And that's kind of why we have that oscillatory behavior. Because, well, if I have a look at what this graph will look like, I don't want to sketch this one because I've got better ones to sketch. Yes. So if we look at the graph of y equals x sine x, it kind of looks like this. So kind of starts down, then goes up, then drops, then goes up, then drops. And that keeps on repeating. And then the same thing happens. This is actually an even function because we have two odd functions being multiplied by each other. And then sort of drops down and comes back up. So we see that when we have composite functions where we have, especially they like to throw this in at interviews where you have a polynomial multiplied by a trigonometric function, we can exploit oscillatory behavior. And that's going to be important later on. The other thing I wanted to touch on is with trig functions is sine of kx and cosine of kx when k is large and when k is really, really small. So you look at this in A level, when k is large, our period is shorter, right? So that means our oscillatory behavior will look like this, right? It'll be very, very frequent. But when k is small, we have a longer period, right? Now, why is that? Well, that's because when k is large, so for example, if we have sine of 100x versus sine of x, and let's say I'm looking between the range of 0 to 2 pi, right? And let's say I'm looking for when between the range of 0 to 2 pi, when sine of x versus sine of 100x is, let's say, equal to 0. So when sine x is equal to 0 is when x is equal to any integer multiple of pi, right? So we're going to have zeros at 0, and we're going to have zeros at pi and at 2 pi. But now sine of 100x, well, if I let theta equal to 100x, so I'd have sine of theta equals 0, that's when, again, theta is equal to an integer multiple of pi. So that's going to be 0, pi, 2 pi, 3 pi, 4 pi, etc., etc. But because theta is 100x, I can fit many more zeros in this range simply because I'm going to be dividing all of the points where sine of x is equal to 0 by 100, right? Over 100, etc. And this will carry on until I end up at 2 pi. Okay. So I'm going to have way more points that's in between the range of 0 and 2 pi for sine of 100. Okay, yeah, so I can essentially have more points in the same interval, right? That's why I have these oscillations that are very close together with a really, really small period, okay? So hopefully that makes sense. And then the inverse can be applied to explain sine of kx when k is very small, okay? Now, why is that important? Well, that's important because, say, for instance, we were sketching something like y equals sine of 1 over x, which I've sketched before. You would have seen that in that video, I used this technique to kind of grapple with how the period is going to change for 1 over x being very, very large and 1 over x being very, very small. Now, we see that as x tends to positive infinity, 1 over x tends to 0. And so our inner function will be very, very small. And we can actually apply the small angle approximation here. So it would be roughly equal to 1 over x. Now, when x tends to 0, 1 over x would actually tend to positive infinity. Let's say we approach from the right-hand side. So that means we'll have a situation where we have sine of k of x, where k is very, very large. And that's why when we tend closer and closer to 0, the period of our function decreases, and so the frequency of our function increases. And that's why y equals sine of 1 over x, if I remember correctly, looks something like this, and then it tends down, and then I believe it's an odd function, so it did something like that, right? And it was bounded between -1 and 1. So hopefully that explanation makes sense. I'm going to use that later on. Classic things like differentiation to find stationary points. You should already know this from your A-level syllabus. But we might want to get into a little bit more detail as to what is actually happening near certain points with our derivative, right? Because we could have a certain function. So say, for example, we have what graph did we... Well, we already had the graph of y equals x sine x, right? And we said it looks like this. Right, it looks something like that. Something like this, right? Okay, cool. Now, if we zoom in here, near 0, can we explain why the graph approaches 0 and gets flatter? So looking at the concavity here, why does it not do something like this? But instead, it comes up, down, and then approaches 0 at an angle. It approaches 0 horizontally. Can we explain that? Well, yes, we can, because we have the tools of differentiation. So, I don't know what's happened to my Miro here. We can explain this by differentiation. So if we have y equals x sine x, that's two functions of x being multiplied by each other. So we have a product of two functions, u and v. So we have to apply the product rule here for differentiation. So I'm just going to do that quickly. Should be a plus. Okay, and now we want to consider the limit as x approaches... approaches 0 of our gradient function, because that will tell us how steep our function is as it approaches 0, right? So that's the limit as x approaches 0 of sine x plus x cosine x. Now we can actually evaluate this limit directly because we don't have any problems here. So this is going to be equal to sine of 0 plus 0 multiplied by cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. 0 multiplied by 1 is 0. And so we have 0. That's interesting. Does that check out? Yes, it does. Because what it's saying is that as you approach 0, at least from the positive direction, and it will be the same because we have an even function here, our gradient is tending to 0. And that's why our function approaches 0 from that angle. It approaches 0 horizontally, right? Now that's important because you could have some functions, like if we zoom in here, like I said, that might approach like this, right? Whereas you might have some other functions that come down like this. Okay? If we're zooming into its end behavior near 0. Or we can do the same thing with near other points as well. Okay, nice. The next thing I wanted to talk about is L'Hopital's rule for evaluating limits. So a lot of people know about L'Hopital's rule, but not a lot of people know when it can actually be applied. So let me just state L'Hopital's rule first. So L'Hopital's rule tells us if we have a rational function and we're considering the limit as x tends to some real number a of f of x over g of x, this is equal to the limit as x approaches a of f prime of x over g prime of x if and only if, right, f of a equals 0 and g of a equals 0, or f of a tends to plus or minus infinity and g of a tends to plus minus infinity, right? And also provided g prime of a does not equal 0. And if it does, you can keep on repeating it and repeating it and repeating it until it does not equal 0. Yeah. So what does that mean? How can you remember this? Well, essentially, if the numerator and denominator of our functions, when we plug in a, tend to the same value, you can use L'Hopital's rule, as long as it's 0 or plus minus infinity. Okay? So for example, if I was considering the limit as x approaches 0 of sine x over x, right? That's tough because, well, let's look at f of x. F of x here would be sine of x, and g of x would be x. F of a, in this case, a is 0, would be 0 because sine of 0 is 0. And g of a would be 0 because g of x is just x. So x is 0. Therefore, we can apply L'Hopital's rule here. So this is going to be equal to the limit as x tends to 0 of the derivative of sine x, which is cosine x, over the derivative of x, which is just 1. Right? And now we can evaluate this limit pretty easily because cosine of x, cosine of 0 is literally 1. Okay? And so the limit as x approaches 0 of sine x over x is equal to 1. If we had something like the limit as x approaches can I think of one? Of x ln x, right? You might be clever and rewrite this as the limit as x approaches 0 of ln x over 1 over x. But now, as x approaches 0, our numerator would tend to negative infinity, sorry. And our denominator would tend towards, so tending to 0, that means 1 over, yep, so it would tend to positive infinity. And so, because the infinities here are of different sign, we can't apply L'Hopital's rule here. So hopefully that makes sense, and that might be important when you're sketching different graphs and you're trying to consider some limits. The other thing is use obvious facts and state them in your interview. So for example, this is a really easy case, but say we had something like y equals the square root of x, right? We know that x cannot be less than or equal to 0 for all real values of x, right? X must be at least 0. Okay? So yeah, think about the domain of your graphs. Don't be silly and start drawing out stuff that's going to happen over here because our graph isn't even defined there. So that's another thing. Think about the domain of your graphs. Another thing I wanted to touch on is, say you had y squared is equal to some function of x. Anytime you see y squared is a function of x, we're going to have reflective symmetry in the x-axis, right? Purely because minus y squared is equal to y squared. I don't know why my mirror is doing that. Let's try and rub this out. Oh, it's not going to rub out. Nice. So we have minus y squared is equal to y squared. Therefore, we have reflective symmetry in the x-axis. Now, why is that? Well, for each x value that I choose, there will be a corresponding y value that is positive and a corresponding y value that is negative of the same magnitude as the one that was positive, right? So for example, if I had y squared is equal to x, this graph, so you can kind of think about it as, oh, y equals plus or minus root x. But that's not really a function. So you'd really just graph y equals root x whoops. You know that any real number squared has to be positive. So I know my x values have to be positive. And so my function is going to look like this. Okay. And it's going to have reflective symmetry in the x-axis. So the top part looks like y equals root x, and this is just y equals minus root x. Okay, so hopefully that makes sense. The other tip I have is sketch the composite functions to help you. So, for example, I don't think I'm going to do any examples in this video. I'm going to just keep on, because I'm going to do a lot of graph sketching for practice. I might just post those later on so you guys can kind of see how I'm working through them. But you want to be sketching the composite functions to help you. So, for example, if I have y equals, this is that simple case that I keep going back to, sine of 1 over x, I would sketch y equals 1 over x, because it would remove a lot of the brain power in my head of keeping on thinking about, okay, when x tends to 0, what's going to happen? Okay, x tends to 0, okay, so y is going to tend to either positive or negative infinity. If I just have my graph and I just sketch it, I know what it looks like, and I can keep on referring to it because I know it's a constituent graph that will help me to build up what my function will actually look like. Same goes for if you have a product of two functions or more functions. So say you are sketching another graph I've seen before, y squared equals x arctan 1 over x. This one's a lot more interesting. I'd probably start out by sketching arctan of, say, theta, and then I'd sketch 1 over x, and then I'd sketch arctan of theta. Then I'll think about, okay, what happens when I sketch arctan of 1 over x? Okay, that's interesting. Now, let's see what happens if I were to multiply my x values by arctan 1 over x at each x and see what happens. So when you're trying to graph harder functions, you really want to think about what are the different constituent functions that are building up my function. What are the actual composite functions that are building up my function? Because that will tell you a lot about how it's going to look and the behavior of the function as x tends to 0, x tends to positive infinity, x tends to negative infinity, etc. Or any other special points. Is there anything else I wanted to talk about? I think I covered all of it. I didn't want to make this video as long as the last one. So yeah, instead of going through some examples here, just stay tuned for more examples. I'm going to be doing some more graph sketches. hopefully going to be posting some more interesting problems that I do. So yeah, do stay tuned for that. Hope you guys enjoyed this one. See you in the next one. Peace.